So we're going to do a review on chapter 18, and this will be the last exam for the semester. On electrochemistry. Go. Get that out of the way. There we go. Okay, number one. Close the door again. For the reaction of sodium bromide with chlorine gas. So this is a word problem where you have to be able to write the compounds in order to answer the questions. Sodium bromide and chlorine gas. Remember, that's diatomic. If you don't do diatomic, then all bets are off. And that yields sodium chloride and bromine. Let's see if I can get it all on this board. Bromine is also diatomic. Okay, so the appropriate half reactions. What we need to do is decide what's happening to who. Sodium is alkaline metal. It's +1, no change to sodium. So we don't care about sodium, it's a spectator. What we're looking at is -1 for bromine here, 0 for chlorine. This is -1 chlorine, and this is 0 bromine. So which one, we look at the way the answers are given. Oxidation first, reduction second. So the oxidation step is going to be loss of electrons. We go from bromine's -1 to 0 is a loss of electrons. But there's another kicker here. What we have to do is balance the equation for atoms and for electrons. So we're looking at loss 1 electron per bromine, but we got 2 bromines. So that's 2 electrons. And that means we need 2 here. While we're at it, chlorine is gain 1 electron per chlorine times 2 equals 2 electrons. So we need a 2 here. And then if you go back and look, there's 2 sodium, 2 bromine, 2 bromine, 2 chlorine, 2 chlorine. So it's balanced for atoms, it's balanced for electrons also. Okay, so when we do the step for oxidation, where oxidation is loss. So we're going from bromine minus, and then the electron for loss goes on the product side. So we're making Br2, but we need 2 of these because we have 2 there. Plus 2 electrons. And the reduction step is the chlorine plus 2 electrons yields 2 chlorines on this side, 2 chlorine ions. Okay, so that should be oxidation reduction. So which one has 2 bromines? Looks like B has 2 bromines. And let's see if the rest of it fits. Yep, that's right. And that's right. Okay. Let's see. Yeah, Corey's still there. He's just not saying anything. Let's see. Scroll up. Got that one also. There we go. Get 2. 2 at 1. Okay, ammonium metavanadate. reacts with sulfur dioxide in acidic solution as follows. The ratio of X to Y is, okay. So let me put that one up here. XVO3 minus Y SO2 yields XVO2 plus Y SO4 2 minus. It's just barely on the screen. Okay. So if we balance this in acidic solution, we've got to separate the, I'm probably going to have to get over on this side of the board. We're going to have to write a oxidation and a reduction step. So we need oxidation states for each one. So this one is 3 times -2 for oxygen is -6, but we're holding out 1. So it's a -5 that has to be balanced. So we need a +5 for that vanadium. This vanadium, that's a -2 here, but it has to be a +2 total. So we're actually looking at a +4 balance. So if we check ourselves, +4 and a -2 is a 2+. So that's good. Okay, now for the sulfurs. This is -4, so that has to be a +4. This is 4 times -2 is -8, but we hold out 2 of them, -6. That's a +6. Okay, so the oxidation step is going to be sulfur. Right? So we got SO2 to SO4 2 minus. I'm going to write these in here so I don't lose track. And the reduction step is going to be the vanadium. VO3 minus, that's a +5, is going to yield VO2 plus, and that's a +4. Okay. So what do we do? Next thing we do is, we okay so far? Okay. Next thing we do is balance the non-oxygen, non-hydrogen. Sulfur, sulfur, vanadium. No trouble there. Now we balance the oxygens with water. So we got 4 oxygens on this side, 2 on that side. So we need 2 more oxygens on this side. Right? 2 more oxygens there. That means we've got 4 hydrogens that have to be added. Yeah, just barely. Okay, let's do that on this side. So we got 1 oxygen there, 3 there. So we need 2 more there. That means we've got 4 hydrogens on this side. Okay, so now we can balance the electrons. This is oxidation, so the electrons have to go over here. Right, it's a loss. So if we go from +4 to +6, we've got 2 electrons on that side. This one, we gained an electron. So we're adding 1 electron on this side. Okay, so far so good? All right, in order to make the electrons balance, we need to multiply this one by 2, and that's it. Right, so once we do that, the electrons are balanced, and we've got a 2 in front of this one, and we've got a 2 in front of this one, and we've got a 1 in front of this one. So it should be X to Y is 2 to 1. See? Okay? We didn't have to go through the whole thing. We just need to get far enough to where we can find out what are the coefficients of those. All right, 3. The following reaction occurs in an aqueous acid solution. In the balanced equation, the coefficient of water is. I'm going to do it over here. Get more room. Okay, so we got to figure out what's the oxidation states. This one's -1. This one, the iodate ion, oxygen is -2 times 3 is -6. We're going to hold out 1, so we need a +5 for this one. For that iodine. This nitrogen, nitrate. So we have 3 times -2 is a -6. Hold 1 out is a -5. So this has to be a +5. How about this nitrogen over here? That's 2 times a -2 is a -4. So nitrogen has to be a +4. Okay, now we can write our steps. So the oxidation step is going to be loss of electrons. Iodine to iodate. Iodine ion to iodate. And this one is -1, and this one is a +5. Okay. Reduction is the nitrate with a +5 here, and the nitrogen dioxide with a +4 means that this has been reduced. That nitrogen's been, we've added an electron to it. Okay, so iodines are balanced, nitrogens are balanced already. So now we can move to the oxygens. This needs 3 oxygens on this side. Now we got 6 hydrogens to go on this side. Here we have 3 oxygens and 2. So over here we need 1 more oxygen. And that means 2 hydrogens. Okay, reduction. We had to add an electron to go from here to here. 1 electron. Over here though, that iodine lost how many? Well, it lost 1 to go to 0, but it lost 5 more to go to +5. So that's 6. Okay. So now we need to balance the electrons. All we have to do is multiply this one by 6. Okay. And all it wants to know is the coefficient of water. So 6 times water would be 6 here and 3 there. Those 3 go away. This one becomes 3. So the coefficient should be 3 for water. Okay. Trying to economize on our time because time is one thing that's in short supply during an exam. 4. Now, the following reaction occurs in basic solution. The sum of the coefficients. Okay, so we're going to have to go all the way to the end to get this one. Yeah, I better put it over here. So this one, element is 0. Element is 0. This one's -2 plus 1. Okay. So we're going from fluorine to fluoride is an addition of an electron. So that's the reduction. So the reduction step, I wonder if this is picking up. Reduction step is fluorine to fluoride. Okay. And let me see, I better give myself some more room here. There we go. And the oxidation step would be what's left over. Water to oxygen. So we went from -2 here to 0. Okay, we need 2 fluorines here. And we need, well, there are no non-oxygen, non-hydrogen, so we move on to the next step. We've got no oxygens here, so there's none to be balanced. But we do have here. So if we've got 2 oxygens here, then we need 2 there, but that means 4 hydrogens. Okay. So now we balance the electrons. This is the reduction step. So we had to add how many electrons? Well, 1 per fluorine, but there are 2 fluorines. So 2 electrons. This one, we lost electrons. Let me do this. I'll put the electrons in here. We went from a -2 to a 0 on oxygen, so that's loss of 2 electrons. But we have how many oxygens? 2. So 2 times 2 is 4. At least it was when I was in school. Who knows what it is now? Okay, now to balance the electrons, we need a coefficient of 2 here. And that'll give us a 2 here, a 4 here, and a 4 there. All right? So we have no water to cancel. The electrons will cancel. And now we can add up our coefficients. So we've got 2, 4, 2, 1, and 4. So 5, 6, 7, 8, 9, 13. 13 is the answer. That way we didn't have to bring it all down before we added them up. That was number 4. Let's see, number 7. A redox reaction, that equation. Which of the following are the correct half reactions? Okay, it looks like this is balanced, right? 2 irons, 2 irons, 2 chlorine, 2 chlorines. So all we need to do is say the oxidation states for iron is 2+ and 3+. That's a 0 for chlorine and 1- for that chlorine. So which of the following are the correct half reactions? Okay. So one of these with the chlorine and one of these with the iron is going to be the correct ones. So let's say, what's the oxidation step? Oxidation means we had to lose an electron. So we went from this iron to Fe2+ to 2Fe3+. And that means 2 electrons. And the reduction step would be the chlorine to the chloride. And that was 1 electron each, but there are 2 of them, so it's 2 electrons. Okay. So when they say the correct half reactions, I'm assuming they want it in the simplest form. Okay. So this one can't be simplified anymore. It's 1, 2, 2, but this one's 2, 2, 2. So the simpler form, the half reaction would be that one. That's what I think they want in this question. So this would be one of them. It would be 4. And this one would be the other one. That 1 and 4. 1 and 4A. And the other reason that I think that's what they want is because this one's nowhere to be found. Sort of a deductive reasoning. All right, I think that one's coming up. I'm going to have to scroll it. Yeah. 8. How many electrons are transferred in the following reaction? Okay, so we definitely need oxidation states here. Iodine's -1. This I2 is 0. This one's 0. That one's -2 plus 1. This one is -1. This one's +1. This one, 3 times 2 minus is 6 minus, hold 1 out, 5 minus, that means this one is +5. So we have all our players. That was not too clear. There. Okay, so how many electrons are transferred? Well, let's see. Who's doing what? Well, iodine is going from a -1 to a 0. So iodine has lost 10 iodines, lost 10 electrons. That should be the answer, but let's check our work. 5 of these +5s went to 0. So that's an addition of 5 electrons. Right? 5 electrons from here to here for each chlorine, but there are 2 of them. So that means 10 electrons. So we're right. 10 electrons were transferred. Okay. Oops. Let's see here. Let's make it go back. Boost it up a little bit. Here we go. 11. Consider a galvanic cell based on the reaction Fe2 plus, dichromate, Fe3 plus, and the chromium 3 in acidic solution. What's the voltage of the standard cell carrying out this reaction? Okay. In order to do the voltage, we need to know which is which half cell. So we've got one half cell. It's probably going from this iron to that iron. 2 plus going to Fe3 plus, which means we have to lose an electron. And then we've got the dichromate, which is 7 times 0 is -14, but we hold 2 of them out, so it's -12 with +12 here, but each one is +6. So we've got, that may not matter actually. Once we identify the players, we just go to the, let's see, +6. This means 2 here. So +6 is 3 like 6 electrons. All right, so this is going to be the cathode. And we'll look up this one as is. This one's the anode. So we'll look it up as this one going to that one and flip the voltage. So we need our, I think it's in the useful information. Better read. Standard reduction potentials. There it is. Okay, so let's do the first one. Fe3 plus reduced. Fe3 plus, Fe3 plus, Fe3. Here it is. Fe3 plus electron, Fe2, 0.77 positive volts. So this is going to be negative volts, right? Because we reversed it. That way it's positive, this way it's negative. This one we can read dichromate to chromium 3 plus. Dichromate. Come on, is it in here? Here it is. Dichromate to chromium 3+, and it's got some hydrogens and water in there. 1.33. This is plus 1.33. Okay, so 7 from 13 is 6, 7 from 12 is 5. That's it, right? 0.55 volts or 56 volts. And that should be positive. There it is right there. Okay. Okay, let's see here. 14. Let's go down here. There it is. Okay, a strip of copper is placed in 1 molar copper nitrate. A strip of silver is placed in 1 molar silver nitrate. So these are in standard conditions, 1 molar concentration. The 2 metal strips are connected to a voltmeter by wires, and the salt bridge connects the solutions. The following standard reduction potentials apply. Which of the following statements is false? Electrons flow in the external circuit from the copper electrode to the silver electrode. Okay. What we have to do is decide which is which is the anode, which is the cathode. Right? And what I do is I look at these and say, all right, if I make this one negative, that's not spontaneous because the sum will be negative. So if I make this one negative, that will make a positive voltage. So that means this one has to be reversed. Copper yields copper 2+ plus 2 electrons. So this one is the anode. And this one is the cathode. So that means that the electrons in the wire are flowing into this cell. These electrons are coming through the wire from that cell. Electrons flow in the external circuit from the copper to the silver. That is true. Okay. The silver electrode increases in mass as the cell operates. Okay. Reduction's taking place and producing silver metal on the electrode. That one is true also. There is a net general movement of silver ions through the salt bridge to the copper half cell. That can't be. Silver ions are not going to move through the salt bridge because they're being consumed to make silver on the, so that one's false. Well, we found our answer. Negative ions pass through the salt bridge from the silver half cell to the copper half cell. Negative ions. Yes, if you're removing positive ions at the electrode, then that leaves an excess of negatives in solution. They got to get out of there. So they move through the salt bridge. And some positive copper ions pass through the salt bridge from the copper half cell to the silver half cell. Some copper ions, yes, because you're building up an excess of copper ions, positive charge on the anode side, and it's trying to equalize, so they'll move through the salt bridge. Okie doke. We found our answer, C. $15. Which of the following species cannot function as an oxidizing agent? Okay, so an oxidizing agent is reduced. Which one of these cannot accept any more electrons? That's the question, right? So sulfur at 0, can it accept electrons? Yeah, it's a non-metal. They love electrons. So this one is, this one will function as an oxidizing agent. How about this one? What's the 3 times -6 -5? This is +5. Yeah, it'll take more electrons. that +5 nitrogen. How about this chromium? We did that one before. I think it's a +6. That one will accept more electrons. How about that iodine? Nope. You don't want no more electrons. So that's the one that can't function. 15, 16. Which metal, aluminum or nickel, could reduce zinc 2 plus to zinc if placed in a zinc 2 plus aqueous solution? Okay, if it's going to reduce zinc 2 plus, then it has to be oxidized. So which one of these flipped to the positive, aluminum or nickel, will give you a positive value? Well, if we make 0.23 volts positive and add them to minus 0.76, we still get a minus. So that one's not going to work. This one, if we make it positive, it will give us a positive value. So aluminum will do it, but not nickel. Does that make sense? Okay. Oops. I need to cut that down just a hair. I'm gonna have to scroll some more after we look at this. Okay, so we've got a galvanic cell. We got a chromium electrode on this side and 0.2 molar chromium 3 plus in solution. And on this side, we have a platinum electrode, which does not participate in the reaction. It's only a conduit for electrons. And the reaction itself occurs in solution, 0.5 molar bromine and 0.1 molar bromide. Okay, those are our starting conditions. And if it's written as it should be, typically, this should be the cathode and that should be the anode. We'll see. Let's scroll down some. So let's take a look at that while we're here. If we leave this one as a reduction on that side and make this one an oxidation, no, it's backwards. That cell is backwards. This needs to be reversed. So this one, as written, is the anode, and this one's the cathode. So it's not following convention. You see how I arrived at that conclusion? Right. If this is the anode, it needs to be reversed, which makes this negative. And that won't work. So it's got to be anode this side, cathode that side. Okay, so let's move it down a little bit more so we can find out what the question is. What is E0 for this cell? E0 would be turning this one positive. So that would be 727 and 1090. 7, 11, 8, 1.817. Should be the answer. Let me go back up and be sure I'm right. Or at least, do I agree with the key? Yep, it's A. We're either both wrong or both right. So I guess you can't always rely on the drawing to be conventional. All right, so let me down here and scroll it up. Okay. Galvanic cell below, The contents of each half cell are written beneath each one. Okay. So this is chromium. This is involved in the reaction. Looks like. Not necessarily. No, it's not. They're using a chromium electrode simply because it's chromium in solution. But this chromium is not part of the reaction, right? This is part of the going from 6+ to 3+. I think. Yeah. So this is 6+ right here, going to 3+. And this one is manganese, and this is manganate, which is -8 instead of +7. +7 to 2+. And I'm not sure which way it's going yet. We have to go further. What's the value of E for this cell? Actually, oops. If you're given the half reactions, if it says E0, that's important. E0 means we can use these values. If it said E with no 0, we have to use these concentrations plus the balanced equation to find out what Q is. Then we could use the Nernst equation to find out what the actual voltage is. Fortunately, that's not part of this problem because that would take some time to do. Okay, so what we have to do is say, all right, which one do we flip? They're both written as reductions. So if we flip this one, that'll make it negative. That one's still positive. We'll get a valid calculation. -1.330 means 671. 0.176 positive voltage. Let's see. C? Is that? Yes. C is the answer. That one?
You'll be using the same graph on the next bunch of questions, just a very different question for each.
Oh, okay. That's good to know. Yeah. What is it asking for? It's asking for when current is allowed to flow, which species is reduced? Okay, we flip this one right here, right? We flip that one. So that means the reaction is going back that direction. So the species that's being reduced is this one because we're adding electrons to it, MnO4. Is another one on this one?
Yep. Or the next one.
Okay. What's the value of Q? Okay. So what we've got to do is reconcile these two in terms of electrons, because at this point, this is a balanced half reaction. Right? 2 chromium, 7 oxygen, 14 hydrogens, and electrons. We have to balance electrons. Right? So what we have to do is flip this one and multiply this one by 5, multiply this one by 6, right? 6 and 5. So we just 6 over here, 5 over here. So that's going to give us, let's see, let's do this side first. 6 MnO4 minus plus 48 hydrogens. We're balancing electrons, so we don't have to do those. And now along with this one is this side of the equation because we flipped it. So this is 10 Cr3 plus and 35 water. There. Okay. And then we're going to have on this side the Mn2 plus. Oops, 6 of them. Almost forgot. And 24 waters. Then we have this side of the equation, 5 dichromates. Right. And then we're going to have, let's see, 5 to 70, right? 70 hydrogens. Did I multiply that right? Yeah, 70. And that's it. Okay, so now we need to reduce the mess. We've got 35 waters here, 24 there. So 24 from this is 11. 11 waters on that side. There's 70 hydrogens there, 48 here. So 48 from that is 2, 22 hydrogens. And can we reduce it any further? Let's see. 6, 10, 11, no. 5. That's it. We can't reduce it any further. So the Q would be based upon these reactants. And it would be an expression of the equilibrium constant only for true values. So we need Mn2, 2 plus, in parentheses, not brackets, because it's not equilibrium. And this is to the 6th power. And then this one is dichromate, to the 5th power, okay? And then hydrogen ions to the 22nd power. All right, so that's the product side. 1, 2, 3, 1, 2, 3. And this side we have the manganate. The manganate. I thought manganate was 2 plus. That's that we looked at one before. This is to the 6th power. And then Cr3 plus to the 10th power. And then water. Water. Oh, water's a pure liquid. Doesn't count. So that's everything. Now we need to plug in values. So the Mn2 plus is 0.2 to the 6th power. The dichromate is 0.3 to the 5th power. Hydrogen ions, wait a minute, throw them. Oh, hydrogen ions are 0.01 to the 22nd power. And MnO4 minus is 0.1 to the 6th power. And chromium 3 plus 0.4 to the 10th power. That's everybody. Yep, now I just have to get a calculator. See if I can do this without making a mistake. Okay, 0.2 to the 6th power. 0.2. Right? And 0.3 to the 5th power, 0.01 to the 22nd power, then 0.1 to the 6th power, and 0.4 to the 10th power. Okay. Must have done something wrong. Unless the answer is none of these. No, it's B. What did I do wrong? 1.5 times 10 to the minus 41. Oh, here it is. Yeah, that's what I got. I got 1.48 times 10 to the minus 41.
So they just rounded them in.
Yeah, this rounded off. Okay. Think you can do that on a test?
Yeah.
Okay. You have to be real careful about the procedure, because if you get anything wrong up here, then that's screwed.
You see, especially with none of these being a possible answer.
Yeah, that's right. Okay, let's put that back over there and move on. Another one? Is it the same one? It's the same one. Okay, what's the question on this one? In a balanced cell reaction, what is the stoichiometric coefficient of H plus?
We said
It was. Let's see, H plus. I can't see it now. Do you remember?
the code, yeah, it was 22.
22.
That's what we had as the, it was to the 22nd power for H.
D. Yeah, okay.
There's one more with the same,
Oh, no.
right?
E. What is the cell potential at 25 degrees as read on the digital voltmeter? Oh, okay. So what we need for this one is the Nernst equation. So E0 minus 0.0591. So minus 0.0591 over N times log of Q. Log of Q. Okay, so E0 was I have to recalculate that one.
1.176.
0.76, okay. So this is 0.176 minus 0.0591. And the number of electrons transferred, that's what we need. 30, wasn't it? Yep. Okay, and then log of Q, which was 1.5 times 10 minus 41, wasn't it?
Yes, yes.
Okay, so that should give us the actual voltage on the meter. Let's see, I'm going to start with the log because it's still in here. So log of that, and then 0.0591 times 30 divide, change the sign, and then 0.176. $0.256 or 0 0.26 volts. Is that right? Is that in agreement? Is what I should say. E? Yeah, okay.
So that's just filling in everything we've done in the last 5 questions.
Yeah, right. Now, if I were to give you this type of question, just as a standalone,
Then you have to.
I'd have to give you these values.
Oh, okay.
Yeah. Maybe not the number of electrons transferred because you could do that from here. But the other part, the Q, that would be a bear of a problem.
Yeah.
To have to go all the way through those other steps just to get to here. All right. Let's see. Looks like we've got a lot of repetition in here. Here's one. The following has a potential of 0.92 volts. Mercury 2 plus, hydrogen, protons, and mercury 1 plus, right? So this is 2 mercuries with a 2 plus, but now this is plus 1. And that's a plus 1. This is a 0. And that mercury is a 2 plus. If the concentrations of the ions were 1 molar and the pressure of hydrogen were 1 atmosphere, then E0 for the half reaction would be well, actually, the atmospheres don't matter. Because if you're only looking at this half reaction, we don't care what's happening to the hydrogens. The E0 for this half reaction, you just look it up.
How is it in the back there?
Yeah. Mercury 2 plus, mercury 2 plus. Here it is. Plus 2 electrons, 0.80. Now, why is that not? Let me see, am I looking at the right one? Maybe I'm not looking at the right one. Oh, I was parallax error. I was reading the one for silver, 0.91. That's right. Okay, so the best answer would be 0.92. So a lot of this stuff is just fluff. We could have easily had just said, duh. Look, this one is standard reduction potential against the standard hydrogen electrode, which is 0. Right? So if this one is 0.92 volts, that one is 0.92 volts because that one's 0.
We literally have the answer in the place on the top there.
Yeah, I didn't have to look it up at all. It's right there. Okay, let's see. Okay, here we go. 44. An excess of finely divided iron is stirred up in a solution that contains copper 2 plus ion, and the system is allowed to come to equilibrium. So I'm assuming that what's going to happen is that iron is going to be oxidized and the copper is going to be reduced. The solid materials are then filtered off, and electrodes of solid copper and solid iron are inserted into the remaining solution. It's allowed to come to equilibrium. What potential develops between the 2 electrodes at 25 degrees? It's a trick question. If it's at equilibrium, the solution concentrations have gone as far as they can in either direction, and the voltage is 0. Okay. 49. You make a cell with an aluminum electrode in a solution of aluminum nitrate and a zinc electrode in zinc nitrate. If you could increase the concentration of aluminum 3+, which of the following is true about the cell potential? Okay. Let me draw a picture here. Aluminum electrode in aluminum nitrate and zinc in zinc nitrate. So zinc would be reduced by zinc is 2+ plus 2 electrons yields zinc metal. That's one of them. Aluminum would be aluminum 3+ plus 3 electrons yields aluminum. Those would be the standard reduction equations. So I need to know which one's which. So aluminum, excuse me, or zinc. So let's find it here. There's aluminum, minus 1.66. Minus 1.66 volts. Reduction potential is minus 0.76. Minus 0.76 volts. Okay, so this tells us which direction is which. This one would have to be inverted to give us a positive. So that means this one's going to be the anode. Aluminum yields aluminum 3+ plus 3 electrons at plus 1.66 volts. Okay, so when we put those together, it's going to be this one plus this one yields this one plus that one. Okay, maybe I should write that out. But it's going to be this one plus this one yields zinc plus 3 plus. Now that's not balanced, but maybe we can answer this without balancing it. If you could increase the concentration of aluminum, which of the following is true about the cell potential? If you increase the aluminum, you're going to try to drive it in the non-spontaneous direction, which should decrease the voltage. It would decrease the voltage. Cell potential would decrease because you're adding product and it's driving the reaction back that way. So the key to this one is to finding out which one's the anode, which one's the cathode. Okay. 56. I have to scroll down a little bit. Go. How many moles of electrons are produced from a current of 14.4 amps in 3.20 hours? This is unit conversion. How many moles of electrons? Okay. So if we start with how many hours it takes. 3.20 hours. Amps is in terms of seconds. It's coulombs per second. So we need to convert this to seconds. Right? 1 hour. How many seconds in an hour? 3,600. Right? 60 times 60. Right? So we got seconds. Now we need amps, which is 14.4 coulombs per second. So we got the hours canceled, the seconds canceled. Now we know the total charge that's being transferred. But that's not moles of electrons. What we need is the Faraday constant to convert coulombs to moles. of electrons. So I don't have it memorized, so I gotta look it up. Let's see, I should have it right here somewhere. Where's the Faraday? Here it is, 96,485. 96 coulombs per mole, 96,485. 96,485 coulombs per mole of electrons. Okay, so that should give us our answer. Let's see, 3.2 times 3,600 times 14.4 divided by 96,485. 1.72, three significant figures. 1.72, there it is, B. Right there. That's how many moles of electrons. Now, that could be useful if you know how many moles of electrons and you know the reaction that's being driven backwards. Then you can say, all right, well, how much metal is being plated out, for instance, because you know the number of electrons, you have the balanced equation, and you can figure like, you know, how much chrome is being plated on the bumper, something like that. Or how much gold is being plated on that pewter ring to make it look expensive. Let's see here. I need to scroll just a hair. Yeah, that's good. 64. What mass of chromium could be deposited by electrolysis? Well, there you go. Of an aqueous solution of Cr2SO4, taken 3 times, from 145 minutes using a constant current of 11 amps. What mass of chromium? All right, so we're going from the, we don't care about the sulfate. We only care about the chromium. So what's the charge on the chromium? Looks like it's a 3+. And that's going to chromium metal. So that means each one of these has to have 3 electrons. For every mole of chromium, 3 moles of electrons. Okay? So now that we know that, we need to find out how many moles of electrons are being transferred. 145 minutes. 145 minutes. We need to convert it to seconds. Seconds, 60 seconds per minute. Let's see. So that gives us so many seconds. Amps. 11.0 amps. 11.0 coulombs per second. That cancels seconds, and these are coulombs. Then we need to convert this to moles of electrons, which would be so many coulombs per mole. 96,485 was it? Here we go. That gives us moles of electrons. Why don't we go ahead? That's moles of electrons. And then convert moles of electrons to moles of chromium. Okay? So for every 3 moles of electrons, you get 1 mole of chromium. So that'll give us the number of moles of chromium in one calculation. And we did that by dimensional analysis. Series of conversion factors. 145 times 60 times 11 divided by 96,485. 485 divided by 3. So that's 0.3306 moles of chromium. So all we need now is the molar mass of chromium. And let's see if I can see that bar. 52.00, rounded off. Okay, so I'll multiply this times 52. And that's 17.2 grams. See, there it is. Okay. Oops.
Okay.
You got it? Okay. Let's see. That's a good point. Oh, okay. 72. Short answer. Oh, I included the worked problems. Okay, balance the following equation. Well, I don't know, would it help for me to do it longhand or just point it out? We have to decide, first of all, what are the oxidation states of each of the players? Didn't we do one of these before? That looks awful familiar.
Yeah.
So reduction, we're going from +6 chromium to +3. So we're adding electrons to make the chromium ion. And then we're taking the iodide ion and going from -1 to +5. And then we've got 6 electrons here, 6 there, so we can add them straight. Just add them straight together. And there's your balanced equation. I don't know what else I could do to make it better. We just follow the procedure.
Yeah, that's how we did the first one that was like that.
Yeah. You just, once you decide reduction and oxidation steps, then you balance the non-hydrogen oxygens, then balance the oxygens with water, balance the hydrogens with protons, and then you balance the electrons. Then you resolve the differences between the two in electrons, and then you can add them together. These are both acids. I wonder if there's a basic one in there. I think there is.
Yep, the last one.
Is this the last one?
Yes.
That was a little easier to read. Okay. So for this one, I use the fake acid method, as I call it, and balance it with hydrogens first. Then once we get to this one, then we take the hydrogens and add hydroxyls. Wait a minute. You know what? This one is a special case. Notice hydrogen ions. So for this one, 6 hydrogen ions. And for this one, we end up with 6 hydrogen ions. The hydrogens cancel. So all you're left with is this base. So that conveniently works out to a basic environment, bismuth hydroxide. We didn't have to neutralize any hydrogen ions for that one. All done. Okay. So how we doing? 220? Sounds like it stopped raining. For a little while anyway.
Yeah, it's a storm all day pretty well. Power to go out.
Yeah, that's it, power. Okay. So we'll be back in for our last meeting next Friday. Knock out that exam
Notebook check.
and notebook check. Yeah. And I think I have to report grades by noon on Monday,
Okay.
but I should have them in bright space, your updated average, no later than Sunday.
This coming Monday?
No,
So next.
yeah, Monday after,
After the next step.
right.
I was like, well, because Corey said something along the lines of the lab reports being due this weekend, so I wasn't sure.
Well, the very last one we did is due today because we have a lab today.
But
But
that one was fairly easy comparatively to the other one, this one, and the first.
sure.
That one's got a little bit more effort.
Formation constant was easier?
Yeah, it just had less, because we did all the math.
Oh, that's right. Yeah. The Ka of acetic acid, that one, what you need to do is graph your points.
That's the only part that takes a long time, is that using, what's it called? Excel.
Yeah.
It's just so difficult on my phone. It took me probably 2 hours to do.
On your phone?
Yeah.
Oh, no, do it by hand.
I think it's better.
Yeah, just do it by hand and staple it.
Gotcha.
It'll look a lot better.
Okay.
And then you can draw in, you can say, okay, here's the equivalence point because it's midway on the steep end of the curve. See, this way, it goes like that. The steep end of the curve, midway steep end of the curve is equivalence point. So you drop it down. Let me just draw it. Wrong color. There we go. So your titration curve is going to be pH here and added base here. And whatever these values are going to be, it's going to start off like this, and then it's going to flatten out like that. And then over here somewhere, it's going to go like that. Like that. So that's that's a sigmoid curve.
Okay.
You see that in biology all the time. It's a growth curve. But in this case, it's chemistry. So this point right here, midway, is the equivalence point. So this is the equivalent volume. Okay. What you want to do is find out what's the half equivalent volume. Right here, 1/2 equivalent. That's right in the middle of the buffer zone. And if you follow this across here, that pH is equal to pKa.
pH is equal to pKa.
At this point, where these cross. And all you have to do then is to use the definition equals negative log of Ka. Okay? So take the negative over here to pKa and do 10 to the minus pKa. And that will be equal to Ka. Now, why does this work? This works because of Henderson-Hasselbalch. pH equals pKa plus log of, let's see, we used acetic acid. So this will be acetate. And this will be acetic acid. Conjugate base, weak acid. And when is pH equal to pKa? These two are equal when this term is 0. Okay? This term is 0 because it's log. It's 0 when this value is equal to 1. Because 10 to what power is equal to 1? 0. Okay, so that's why we go over here at half equivalence. At half equivalence, you've only neutralized half of those. If you neutralized half of those, that means you produced an equal amount of these. That's why we want to come to half equivalence, and that's when the conjugate base and the acid are equal concentrations, right at that point.
Gotcha. That'll help fill in the lab report.
Yeah, and just do as good a job as you can on drawing the graph to demonstrate that you know what's what. And remember, all graphs have to stand on their own 2 feet. Right? A graph has to have everything. Title, label the axes, anything else you want to say in it, even captions of any kind that you want to say extra stuff. It has to stand alone. Okay. That means we're done for today. And let's see, I don't remember if I told Corey if he came in late. We're not having a lab today. That means no report is due on electrochemistry. Lab.
Why happened to not to lab?
Right, we're not going to make a battery today. So the last lab that's due is the formation constant. We were talking about the next to the last, the Ka, and then the formation constant is the last one that we've done that you need to report. Then when you come in next week for exam, bring your notebook so I can check it out. That's it.